Welcome to Logistic Regression. This is our final video class, Class 9. Thank you for sitting through the other classes. We're going to be talking about logistic regression in this class, naturally enough. Now, logistic regression is a little bit harder, I think, to understand if you're a psychologist than a lot of other types of regression, mostly because logistic regression deals with odds ratios, and odds ratios are a little bit hard to get your head around. It's a little bit different way to think. Odds ratios can be very large and still be non-significant, but it's not. We're not used to talking about odds ratios. Odds ratios are much more common in the medical sciences. Maybe if you're in a biological psychology area or a neuropsychology area, but less likely in most of the other areas of psychology. But still, it's worth knowing about because logistic regression gives us a way to handle outcome variables that are categorical, either dichotomous or uh, more categories. So, okay, so here's an odds ratio situation. We have two groups. We have cases and controls. They're listed at the top. Our cases are people who, well, this is New Year's Eve. So cases are going to be people who are on New Year's Day, come to a clinic and they're hungover. Controls are people who come to the clinic for some other reason. And then we have exposure. Exposure would be people who ate before drinking and people who did not eat before drinking. And so then we have our counts. We have 13 people who were hungover, 17 people who were hungover did not eat. For controls, we have 32 people who ate, and for controls, we have 23 people who did not eat. And now if we look at this, we can say, well, we calculate our odds ratio, which is A divided by C divided by B divided by D. So it's 13 divided by 17 divided by 32 divided by 23. That comes out to 0.55. In this case, we can say that what that means is if you ate on New Year's Eve, you were half as likely, about 55%, but about half as likely to be hungover as if you did not eat. Now, what gets complicated here is the interpretation of that odds ratio does depend upon the specific kind of study we're doing. So it does depend upon the specific kind of study that we are in fact doing. So what's an odds ratio? An odds ratio is a measure of association between an exposure and an outcome. The odds ratio represents the odds that an outcome will occur given a particular exposure compared to the odds of the outcome occurring in the absence of that exposure. And odds ratios are most commonly used in case control studies. However, they can also be used in cross-sectional and cohort study designs as well, with some modifications and or assumptions. Now, that's why we don't use it very often in psychology. In psychology, we're usually doing cross-sectional or cohort studies. We're usually not doing a case control study. So the interpretation gets a little more difficult, but not really that much more difficult. Odds ratios are used to compare the relative odds of the occurrence of the outcome of interest, e.g. disease or disorder, given exposure to the variable of interest, e.g. health characteristic aspect of medical history. The odds ratio can also be used to determine whether a particular exposure is a risk factor for a particular outcome, and to compare the magnitude of various risk factors for that outcome. So if the odds ratio is 1, it means the exposure does not affect the odds of the outcome. If the odds ratio is greater than 1, then the exposure is associated with higher odds of the outcome. And if the odds ratio is less than 1, exposure is associated with lower odds of the outcome. You can also set up a confidence interval around odds ratios. The 95% confidence interval is used to estimate the precision of the odds ratio. A large confidence interval indicates a low level of precision of the odds ratio, whereas a small confidence interval indicates a high precision of the odds ratio. It is important to note, however, that unlike the p-value, the 95% confidence interval does not report or measure statistical significance. In practice, the 95% confidence of an interval is often used as a proxy for the presence of statistical significance if it does not overlap the null value, which in this case, the null value is not 0. The null odds ratio value is 1. Nevertheless, it would be inappropriate to interpret an odds ratio with 95% confidence, with a 95% confidence interval that spans the null value, as indicating evidence for lack of association between the exposure and the outcome. Let me repeat that. Nevertheless, it would be inappropriate to interpret an odds ratio with 95% confidence interval, with a 95% confidence interval that spans the null value, as indicating evidence for lack of association between the exposure and the outcome. All right, well, here we go. Here's a interpretation of the odds ratio within logistic regression. So the odds ratio in logistic regression. When a logistic regression is calculated, the regression coefficient B1 is the estimated increase in the log odds of the outcome per unit increase in the value of the exposure. In other words, the exponential function of the regression coefficient is the odds ratio associated with a 1 unit increase in exposure. What makes this a little harder to understand is you have to understand the different types of designs to understand the actual interpretation. So we actually have 3 types of designs, although some people argue there's only 2, but we'll say there's 3. You have the cohort design, and that's where you study a cohort over time. That would be our typical psychology type of study. You get people, you assign them at random to treatment, and then you see what happens from the treatment, what conditions they end up having. A cross-sectional design is you take all the data at one time. So you take people, you see what condition they have and what exposures they've had. But with the case-control design, which you mostly see in medicine, you might see in clinical situations or in neuropsychology, you have a group of people that have some disease or disorder. Then you go out and you find a control group. Then you look at the control group and the group with the disorder, and you say, what is the difference in the exposures that they've had? And this is mostly used with rare diseases or disorders, where if you just did a random sampling, well, obviously you can't give people those rare disorders or diseases. But if you were just to do a cross-sectional design, you wouldn't end up with enough people with those rare diseases or disorders to do your study. So you go out and get people with the group individuals who have that disease or disorder, and then find a matching control group. Then you look backwards at the exposures. And if that doesn't make sense, I have another example here for you. I borrowed this cute little chart, and it shows the different types of designs. Now you can see we have our investigator. Researcher begins their research when the researcher enters the scene. We have, is it present, is it absent, and then we have a question mark, what we are seeking, the information we are trying to obtain, what we do not know, our question. So we have here the case control design, and that's the one we just talked about, okay? And in this kind of design, the researcher is looking for prevalence within the study. So this is good for rare diseases. So what you do here is you can see the time interval. The people have had the exposure, but we don't know what the exposure was. They've had the disease, and now the researcher is entering the situation. And so they find people with the disease. They then find a control group, and then they look backwards to see what they were exposed to. With the prospective cohort, what you do is you have people who have been exposed already. The researcher comes in, and then the researcher looks to see whether disease develops in those groups. And as it says, that's sometimes used to test out a new intervention or treatment. So actually, in that case, we could probably put the researcher back here, because the researcher is giving the 2 groups the exposure. Gives one group the exposure, does not give the other group the exposure, and then sees if the disease, if the individuals end up having the disease. In the other case, which they're calling a retrospective cohort, which is more similar to our cross-sectional design, we have individuals who have had the exposure and have not had the exposure. and then we look to see whether they've developed the disease or not. And that's sometimes called a retrospective cohort. So that's another way to look at the design, at the designs. But what's clear is in this case control situation, which is very different than what we normally do in psychology, the researcher is looking at individuals who already have the disease and then looking back to see what their exposure was, if that makes sense. Mhm. So I think this is even easier to look at. Again, this is using similar but slightly different terms. With the cross-sectional design, you're in the present and you're looking for both disease and exposure in the present. So that would be when we take, for example, a number of students, say we wanted to study whether eating some type of food led to increased anxiety. With the cross-sectional study, we would just give out a survey to a lot of students and we would say, what do you eat and do you have anxiety? With the cohort study, what we do is we take individuals, we ask them to eat something or give them that food to eat, and then we look in the future to see if they develop anxiety. In the case control study, present is cut out here, but present would be disease. In the case control study, what we do is we go out and then we go to a clinic and we find individuals who are anxious, and then we find a control group, and then we say, did you eat this food or not? Okay, so cross-sectional design, the type of survey study we do a lot. We give a survey to a lot of individuals. We say, uh, do you have this particular disorder or disease? And, did you take these drugs? Did you eat these foods? Did you have these treatments? The cohort design would be the true experiment, or at least quasi-experiment. We take a group of people, we assign them at random to treatment or exposure, and then we see if they develop some disease or disorder. Again, the case control, and it's usually used with rare diseases or disorders. We find people who already have the disease or disorder in the present, and we then ask them or look back to see what kinds of exposures or treatments or interventions they had, what kind of foods they ate, what kinds of drugs they took, whatever it might be. So we're looking backwards. Okay, so I hope that makes some sense. Given that existence of different kinds of designs, we're not going to look at logistic regression. We're going to start with, again, Andy Field's slide. Okay, when and why do we use logistic regression? We use it to predict an outcome variable that is categorical, or perhaps dichotomous, from one or more categorical or continuous predictor variables. So we use it when the outcome or the dependent variable is not continuous, but is in fact categorical or maybe even dichotomous. Now, I should say here, I don't think Field mentions it. It should really be a dependent variable. If your categorical variable is a independent variable, then you probably shouldn't be using logistic regression or regression at all, or at least you should be using a regression where you turn the regression around. So your y is supposed to be a dependent variable. If your y is really an independent variable and not a dependent variable, then you shouldn't really be using logistic regression. I say that because some people actually use logistic regression to predict what's really an independent variable, and you should not be doing that. I mean, the statistical procedure doesn't know if it's an independent or dependent variable in reality, but you do. Okay, but anyway, so you're predicting a dependent variable or an outcome variable that is categorical from one or more categorical or continuous predictor variables. It's used because having a categorical outcome variable violates the assumption of linearity in normal regression. With one predictor, this is just an expression of the model or the regression line. So if we only have one predictor, this is going to be an expression of the regression line. And if you want more information on this, please turn to field. So what we're really doing is we're predicting the probability of the outcome occurring. So that's why, again, odds ratios are relevant. What we're doing is we're predicting the probability of the outcome occurring. So if it's a dichotomous outcome again, for example, if it's an outcome like developing a disease or not developing a disease, we're predicting the probability of developing the disease. So MBO or B sub O, B sub 0 and B1. So B sub 0 and B sub 1 can be thought of in much the same way as in the linear model. One is B0 is a constant and B1 is a weight that's multiplied times each predictor. B1 would be the first predictor, but B1 is multiplied times the first predictor. And note, the linear model equation forms part of the logistic regression equation. Of course, this would be the formula if we have several predictor variables. Note, we're still predicting the probability of an outcome occurring. The difference, note the linear model or the linear model equation still forms part of the logistic regression equation. So that's really not a difference. The only difference is this is expanding. This is expanding to include more terms, to include additional predictors. That's really the only real difference. In logistic regression, we get a log likelihood statistic. And this is the log likelihood statistic. You can see it here. And I don't expect you to memorize this. I don't even expect you necessarily to understand each component of it. Basically, or make it more simple, it's analogous to the residual sum of squares in the linear model. So it's similar to error sum of squares in the linear model. It's an indicator of how much unexplained information there is after the model has been fitted. And if this log likelihood statistic is large, it means you have a poorly fitting statistical model. We can also get a deviance statistic. The deviance statistic is very closely related to the log likelihood. It's given by, now this is not a negative sign here. Okay, this is not a negative sign. Maybe I'll correct this slide so you don't even see the negative slide when you actually see this video. But in field slide, there's a negative. It looks like a negative slide. That's just meant to be a bullet point. So the deviance statistic is equal to a -2 times the log likelihood. So the deviance statistic is equal to -2 times the log likelihood. And again, I don't expect you to necessarily know a lot about this other than, I just wanted to explain what this deviance statistic is. Again, if you turn to field, and I don't know what you went through in your first semester, field actually starts with the chi-square and then more complicated models for looking at odds ratios before getting into logistic regression. If you want to read over some of that, it might help to explain some of these, understand some of these things a little bit more. I'm not going to go into a lot of depth on this because to a certain extent, I don't think it's necessary for you to know in terms of understanding the basics of logistic regression. Also, it's probably unlikely that some of you may ever run logistic regression, so I'm not going to go into a lot of depth here. But, Field goes through a lot more explanation, takes you through all of this in his book if you want to go through it. So it's possible to calculate a log likelihood or deviance for different models, and then to compare these models by looking at the differences between their deviances. So the deviance statistic almost serves like R-squared change. It allows you to look at or to compare different models. You also do get an R and an R-squared from logistic regression. The R statistic is the partial correlation between the outcome variable and each of the predictor variables. It's going to vary between -1 and 1. So it's very similar to the R in a normal regression. So it's very similar to the R in a normal regression. And this shows you what gives you the R statistic. And of course, I should have mentioned before we left the last slide, if you want to calculate R squared, you can just take that R value and square it, as we'll see. There is something called the Wald statistic. The Wald statistic, your Z or standardized value just equals your B divided by the standard error of B. So if you take your estimated B and divide by the standard error of B, you get a Z that corresponds to the Wald statistic. It's very similar to the T statistic in the linear model. It tests the null hypothesis that your obtained coefficient equals 0. It will be, as Field notes, biased when B is very large. But if B is very large, you probably don't care because it's going to be very significant. It's better to look at likelihood ratio statistics than to look at this Wald statistic. You do get also an odds ratio. Your odds ratio is going to be the odds after a unit change in the predictor divided by the original odds. So in this case, your odds ratio that you get will be the odds after a unit change in the predictor divided by your original odds. So it indicates this odds ratio change indicates the change in odds resulting from a unit change in the predictor. So if the odds ratio is greater than 1, as the predictor goes up, how much does the probability of the outcome occurring go up? If the odds ratio is less than 1, as the predictor goes up, how much does the probability of the outcome occurring go down? Although I'll note again, one of the problems with all of this is whether your odds ratio is greater than 1 or less than 1 is going to depend on how you set up those rows and columns. So I always advise people to go back to the actual percentages in the cells to see what the odds ratio means, or in this case, the changes in odds ratios. Because depending upon how you set things up, you can get different, the odds ratio can be greater than 1 or less than 1 because sort of you change the problem, if you're following me. So depending on what, in logistic, that's true in a simple contingency table. It's also true in a logistic regression. So in a logistic regression, what you give the value 0 and what you give the value 1 is going to determine whether the odds ratio is greater than 1 or less than 1. So in the simple dichotomous case, what you assign a 1 and what you assign a 0 is going to determine whether the odds ratio is greater than or less than 1, if you're following me. Okay, it's going to depend upon which value you arbitrarily assign to 1 or 0. Or in a multi-category situation or a multinomial situation, how you assign those values. Building the model. As with the regressions we've covered before, as with regression with multiple predictors, there are different ways to enter the variables. So for example, you have forced entry, where all variables are entered simultaneously. You have hierarchical entry, where variables are entered in blocks. Again, if they're in blocks, it should be based on past research or the theory being tested. And hierarchical tends to be Field's favorite approach. You can do stepwise. The variables are entered on the basis of statistical criteria, i.e. the relative contribution to predicting outcomes. Again, Fields isn't a big fan of this, argues it should be only used for exploratory analysis. Although I might argue it's sort of like machine learning. Model building and parsimony. When building a model, we should strive for parsimony. That is, predictors should not be included unless they have an explanatory benefit, which gets back to my argument before that some people would argue that unless a predictor variable is correlated with the outcome variable, you probably shouldn't enter it into the regression equation, or in this case, the logistic regression equation. So first fit the model that includes all potential predictors, and then systematically remove any that don't seem to contribute to the model. So here, Field is sort of suggesting a backwards approach, putting all the variables in first, and a very exploratory approach. I'm not sure how this ties into with standard regression, the argument that it should be based on theory and should be hierarchical. I would probably say it should be based on theory and hierarchical, just like basic regression. Things that can go wrong with logistic regression. Of course, we have the assumptions from linear regression: linearity, independence of error, and multicollinearity. And we also have some unique problems, what's called incomplete information, complete separation, and over dispersion. Incomplete information is just that some cells may be missing. So some cells from the predictors may be missing. So say we're looking at whether smoking or eating tobacco or smoking or eating tomatoes leads to cancer. No, not eating tobacco, but smoking or eating tomatoes leads to cancer. What you can see is a problem where one of our cells is missing. And actually this can happen quite a bit. So one of our cells is missing. For people who do not smoke and do eat tomatoes, we have no one with cancer. So that cell is missing. So we have basically a situation where our design's really unbalanced. We have a missing cell. That's going to cause a problem for logistic regression, that we have this missing cell. So categorical predictors predicting cancer from smoking and eating tomatoes. We don't know what happens when non-smokers eat tomatoes because we have no data in the cell of the design. I'll note that's one of the problems with training studies. My friend Winfrey Arthur does a lot of training studies where he looks at the training modality or the training approach, for example, different, lecture versus textbook versus computer-based training versus having groups work on activities. And so different training modalities, and then different types of or different things that you want to train. For example, maybe training leadership versus training knowledge and psychology. Stop there. Go ahead and stop. The next problem that Field notes is what's called complete separation. You can see complete separation here. Complete separation is when the outcome variable can be perfectly predicted, e.g. predicting whether someone is a burglar, your teenage son, or your cat based on weight. Now, the problem, I think, here is a little different than what Field says. Now, Field says the problem is that you have a interval of weight where you don't have predictions, which I think is true. That's true. But the other problem is that your model is completely deterministic. So if you're not familiar with completely deterministic, that means, it means it's really not a probability model. This is a probability model. This is a completely deterministic model. By completely deterministic, we mean that there's only one of two states. You can perfectly predict the outcome or the state. And when you can perfectly predict the outcome or the state, it's referred to as deterministic. It's no longer a probability model. Since there's no probabilities, there's nothing, in a sense, to predict from in terms of the probability of being a burglar. It's completely deterministic. So if you're following me, it's completely determined, the result. There's no error. There's no lack of confidence in predicting the result. You perfectly know the result. That's what's called a completely deterministic model. So it's no longer a probabilistic model. It's a completely deterministic model. To me, that's the real problem here with complete separation. It's not that it's complete separation, it's that it creates a completely deterministic model. Then we come over dispersion. Over dispersion is when the outcome occurs when the outcome contains more than two categories. Over dispersion was where the variance is larger than expected from the model, and this can be caused by violating the assumption of independence. Field doesn't really understand totally. He admits over dispersion. I don't understand over dispersion totally. I will admit I believe it occurs. To me, I think it's occurring because you're violating the assumption of independence. Uh, I think what happens a lot of times if you have more than one category, I mean more than two categories, so your variable is not dichotomous, but you have multiple categories, you end up with people who are in more than one, who choose more than one category, and you code them that way, and that violates the assumption of independence. So let's say you're coding race or ethnicity, and you allow people to choose multiple races. So you have people, for example, who choose Hispanic and white, or Hispanic and African American, or you have people who choose Hispanic, African American, and Asian American. In that case, you're violating the rule of independence. You can only allow people to make one choice if you're going to use a chi-square or this type of regression. I mean, in real life, people can be allowed more than one choice, but for the statistical analysis, they can only be allowed one choice. If they're allowed more than one choice, it's violating the assumption of independence. So independence means each person can only have one choice. They can't have more than one choice. If they get more than one choice, it's going to violate the basic assumption of independence, and it's going to mess with your modeling. And so I think that's what leads to over dispersion. But I could be wrong because, again, I'll say I don't really understand. As Fields says, he doesn't really understand over dispersion. Perhaps it occurs in other fields other than psychology or something like that. Again, as I said, in psychology, we don't really use logistic regression that much anyway. So I don't know what over dispersion means. But the problem does make the standard errors too small. Okay, the process, running a logistic regression. To run it, we go again in SPSS. So we're going to use SPSS. We're going to choose along the top menu regression, or we'll analyze first, of course. We choose analyze. We go to regression again. Then we go to binary logistic, or we can go to multinomial logistic. So we have one of two choices, binary logistic or multinomial logistic, depending upon whether the dependent variable, how many categories and other factors the dependent variable has. We're going to only deal with the situation where we're running binary regression or binary logistic regression. The process is and here again, Field gives you one of these handy charts, which shows you the process, including what to do when various things go wrong, looking at your diagnostics, checking for interactions, checking for multicollinearity, etc., looking at your residuals. So the typical things you would do and what to do about them if they go wrong. His advice is probably a little different than with the linear regression, but again, I think this chart is helpful. So he then goes through an example. The example is predictors of a treatment intervention, or predictors of the success of a treatment intervention. The participants are 113 adults with a medical problem. The outcome is whether you're cured or not cured, 0 or 1. So it's a dichotomous outcome. And as I said, we're just going to deal with dichotomous outcomes in this class. I'm not going to get into more complicated kinds of outcomes. The predictors are your intervention, whether you got a treatment or not, and your duration, the number of days before treatment that the patient had the problem. So the duration, the number of days before the patient received the treatment that they had the problem. And then, of course, we're looking at whether they were cured or not cured. We actually, Field's going to use a third predictor, which is the interaction of interventions and duration. So we can see some of the output. Again, if you go to Field, he goes into great depth on this output. The dependent variable encoding, not cured is a 0, cured is a 1. The categorical variables coding, we have for no treatment, there's 56 no treatments, that's coded 0. We have 57 interventions, that's coded 1. Then it goes through the initial analysis. Now it helps to understand here that Field runs again. Field actually has 3 predictors loading it in at 3 different models. So the predictors are going to be the intervention, the duration, and then the interaction of intervention and duration. So Field actually has 3 predictors here: intervention, duration, and the interaction of the intervention and duration. I just want to check and make sure. Yes, he puts in intervention first. So he puts in intervention first, and then he puts in intervention and duration. So intervention is going to go into first into this model. Now, if you're a diligent reader of Field's book, you'll note in Field's book, he is going to go through all 3 of these models. So Field actually does 3 models: the intervention and the duration, and the intervention, duration, and the interaction of the intervention and duration. But if you read Field, you know that the duration is not significant and the interaction is not significant. And you can see that here. The increase for these 2 models is not significant. And so we are not going to go through model 2 or model 3 just because for time and because it's not significant anyway. We're just going to look at model 1 and we're going to skip model 2 and model 3. But in Field's book, he does go through model 2 and model 3 and, of course, reports that they're simply non-significant. He then goes through it gives you, I don't really know what, I myself wouldn't really use this, just the iteration history at step 0. I guess it's could be interesting if you wanted to look at it. It tells us how many steps, in a sense, it goes through. What's more useful, I think, is the model summary. So we get the log likelihood measure. We get an R-squared measure. We actually get 2 R-squared measures. And then I think what's probably most useful for us is this classification table. So we're starting with step 1. And we can see in step 1, this is the number of people that were observed. This is, again, a 2x2 contingency table. It's showing us, in terms of the observed values, how many were not cured and cured. And in terms of the predicted values, how many were cured and not cured. And so you can see among not cured people, we correctly predict that 32 were not cured, but we incorrectly predict that 16 would have been cured. Among cured people, we incorrectly predict that 24 would be not cured, and we correctly predict that 41 would be cured. If we want to look at the percentages, correct, among not cured people, we can correctly predict non-cured people 66.7% of the time. We correctly predict cured people 63.1% of the time. And our overall level of correct prediction is 64.6. So our overall level of correct prediction is 64.6. I'll leave it up to you to judge whether that's good or bad. Then we go to the model parameters. We can see at the first step again, we put in the intervention. We can see our b-value, which is hard to interpret, I think, what that really means. But we can see that both the constant and the b-value, standard errors for the b-value, Wald measures for the b-value, or Wald measures for actually the effect of the intervention, the degrees of freedom, the significance. So intervention is significant. The p-value associated with it is 0.002, which would be significant at the 0.05 level. And then you can see the odds ratios. Again, the odds ratios for the constant doesn't really matter that much. The odds ratio for the intervention would be 3.417, which is saying that your likelihood of being cured is about 3.4 times higher if you've had the intervention. Although, again, one of the complexities here is that's really going to depend upon the kind of design you have, how you interpret that, and the exact interpretation of that is going to depend upon your design. But you can see again the lower and upper confidence intervals for this odds ratio. Again, the null hypothesis is a 1. So if the lower confidence limit includes a 1, then this should be non-significant. In this case, the lower confidence limit does not include a 1. And so, of course, it is significant. And then we can see our bootstrap of our values. So now that we can see our bootstrap of our values, it's not bootstrapping the odds ratio, it's just bootstrapping this B value. But again, you can see it's significant right here. Okay, then he gives us a model summary. Here's our R, 0.22, our R squared, 0.06, shows you how it was calculated. And he gives you this classification plot. Again, I'm not a very graphics or visual person. I don't find this classification plot particularly helpful, but it sort of helps you visualize or see how many correct classifications you have. All right, in summary, the overall fit of the final model is shown by the deviance statistic. Again, the deviance statistic is -2 times that log likelihood statistic, and its associated chi-square statistic. If the significance of the chi-square statistic is less than 0.05, then the model is a significant fit of the data. Check the table labeled variables in the equation to see the regression parameters for any predictors in the model. Look at the Wald statistic and its significance. Again, that Wald statistic is a little bit like big B beta. It's like a standardized B. And use the odds ratio for interpretation. If the odds ratio is greater than 1, then as the predictor increases, the odds of the outcome occurring increase. If the odds ratio is less than 1, then as the predictor increases, the odds of the outcome occurring decrease. And of course, the confidence interval for that odds ratio should not cross 1. Then Field goes through how it would report the results. In terms of reporting the results, the reporting the results we can see in table 19.3, Field's suggestions. Again, it's similar to our standard regression model. Field would suggest or proposes reporting the B value, both the constant and the intervention, and you can see he gives you the bootstrapped confidence intervals. Then the confidence interval for the odds ratio, this would be the odds ratio, this would be the lower limit, the upper limit. Then the various R squares and the model chi-square. So that's what Field suggests. At this point, we're going to go back to our own study, the COVID data. And we're going to look at a new question, though. We're going to ask the question of, does the governor of a state, the politics of a governor of a state, reflect the age of the population or the region or both or the interaction? So we might be interested in, can we predict the political party of a governor from how old the people are in the state on average and whether the state is in the north or south? And of course, we can also load in the interaction. So we use that database I've already collected, which has all this information in it. And I'm not sure why this slide is a little blurry. It makes no sense that it would be blurry, but it is. Apologize for that. But so we can see again, we have 50 states. And we know the political party of the governor in each state. We know the average age, and we know whether it's in the north or south. In terms of our dependent variable encoding, a Republican is coded as 0, a Democrat is coded a 1. So maybe I better write that down for myself, Democrat 1. Then we also have north-south. South, there's 17 states that are officially in the south, although I added a couple actually, and there's 33 that are in the north. And you can see south was coded 1 and north was coded 0. All right, here is our output again for the variables in the equation, which in this case is just average age. And you can see it's giving us our B coefficient, which is 0.259, and also our constant. It gives us the standard error. It gives us the Wald statistic. Now again, this Wald statistic, it's similar to a standardized B, but in saying it's similar to standardized B, it's also similar to Z or a T. It's giving you something equivalent to the T statistic in standard regression. So you would think if it was this large, it would be significant, although it's not significant. The degrees of freedom for the statistic and the significance 0.073. Again, that's the probability or the p-value 0.073. So in this case, this would not reach traditional levels of significance. Our odds ratio, 1.295, which could be interpreted as the increase in odds with increasing units of age. The confidence intervals have been cut off. So just to make it a little clearer and larger, I didn't put the confidence intervals on here, which other times I do put them on and make it less probably clear, less easy to read. So I'm not sure why I did, but I did cut off the confidence intervals. You can see I actually did print them out. And the confidence interval for this odds ratio does include 1. So again, remember the null hypothesis is not 0. The null hypothesis is the odds ratio will be 1. So if the confidence intervals overlap with 1, it means the result is non-significant. And in this case, the confidence interval did overlap with 1, which meant it was non-significant. The test on the model coefficients, you can see basically it is again non-significant, 0.052. In terms of our classification table, it's step 1. You can see for this again would be the observed values. We have our standard 2x2 contingency table. We have observed, we have predicted. For observed Republican, we correctly predict 18 of the Republicans. We incorrectly predict 8. For observed Democrat, we correctly predict 11, but we incorrectly predict 11, but we correctly predict 13. So incorrectly 11, correctly 13. That gives us a percentage correct of 69.2 for Republicans and 54.2 for Democrats. So for Democrats, we're not doing much better than a coin flip. Okay. This will be our next piece of output. And there's a little bit of a strange labeling, I think, here. Again, I told you I used forced entry. Because I used forced entry, this is actually labeled block 2. So this is step 1, but it's sort of step 2. But the way SPSS labels them, this is block 2, step 1. So this is block 2, step 1. In our forced entry, it's really the second thing we're doing, though. And so now we already have average age in, and we're loading in north-south. And of course, we also have the constant. And since north-south is the important addition, you can see that north-south, here's the B value for north-south, standard error, Wald statistic. It just barely reaches significance, 0.048. And then you can see the associated odds ratio. And again, I cut off the confidence intervals, but this confidence interval just barely starts below 1. So this confidence interval just barely starts below 1. Again, average age, b-value, standard error, Wald statistic. You can see it's not significant. And the odds ratio, and again, this odds ratio, the confidence interval, does include 1. So we would see average age as not being significant, but the region north-south as being significant. Okay, so now we have our new classification table. In our new classification table, it is a little better. If we look at it, we can see that for political party observed, for Republicans, we correctly predict 16 as being Republican, incorrectly predict 10 as being Democrats. Now for Democrats, we've improved a little bit, though we now correctly predict 16 as being Democrat, but incorrectly predict 8 as being Republican. But our percentage correct is 61.5 for Republican and 66.7 for Democrat. I'll leave it up to you again to judge whether you think that's that much of an improvement over 50-50. I did try to put in the interaction. You can see here I put in the interaction. It wasn't significant when I put in the interaction. So I did put in the interaction. You can see it's not significant. You can see something else though. The odds ratio for the north-south region sort of blows up. As a matter of fact, it goes from, the confidence interval go from 0 to some incredible value. That's because of this multicollinearity that's introduced by putting in the interaction. So because of the unique nature of this data, it just so happens that if we put in the interaction, it's highly correlated with the region itself. As a result, we have huge amounts of multicollinearity, and the data analysis really doesn't work. We violated the assumption, it doesn't work. So this is a good example to end up with of what happens when you violate assumptions. By violating an assumption and by having a large degree of multicollinearity, we get really uninterpretable, almost borderline wild results. You know, it basically just blows itself up. Okay, and just to help you out a little bit here in understanding that the north-south effect, I actually just did a simple crosstab. So I went back and said, you know, I said to you a lot of times if you do a simple crosstabs, it helps you see what the logistic regression is showing you. And so here we have north-south, and we have the political party of the governor. And you can see that in the South, 70.6% of governors are Republican, only 29.4% are Democrat. In the North, it's a more even split, 42.4% are Republican, 57.6% are Democrat. But if you just look at this, you'd say, hey, there's a correlation between region of the country and whether you're a Republican or a Democrat. And in fact, then if we were to run the chi-square and the odds ratio, we get something very similar to what we got from our binary logistic regression. That is, the odds ratio for north-south is 3.257. Now here it does include 1. It does go down to 0.932 and goes up to an upper confidence interval limit of 11.380. But so our odds ratio is sort of similar to what we got from the binary logistic. And so we can see that the odds of being Republican increase if you're from the South. So the odds of being Republican increase if you're from the South, or the odds of being a Republican governor increase if you're from the South. Okay, that brings us to the end of binary logistic regression. Again, there's a lot more things you could cover. You could probably teach a whole class, a course on just logistic regression. We're not going to. There's a lot of things I'm leaving out, admittedly, with logistic regression. But this was really just to sort of give you a taste. And plus, it's our last class for this course. So I think it's an appropriate point to end right here. Thank you for sitting through our PowerPoint lectures. This brings us to the end of the PowerPoint lectures. Again, if you have any questions, any inquiries, bring them to the discussion group, or you can always email them to me at DennisStoverspike, that's one word, @gmail.com. Thank you very much. And Happy New Year. Today is actually New Year, recording this on New Year, so Happy New Year. Happy belated New Year, probably by the time you're watching this.